Students, in the last segment, we learned that if we have to arrange n different things in n different slots, linear way, then we have total n factorial ways to arrange them. For example, if we are given 6 slots or chairs in a linear pattern and we have 6 different persons, in how many ways can we arrange them in those slots? As we know from this, there will be 6 factorial ways, right? So now if I ask you that what if we were asked to arrange all of these 6 persons in a circular fashion, will there be equal number of ways? Will it be 6 factorial? No, the total number of ways in which we can arrange 6 different persons in circular fashion will be 6 minus 1 factorial, that is 5 factorial. So why is it so? To answer this question, we have to get back to the previous example. At first, we see that the first person who will sit in these slots will have how many options? 6 different options, right? So he can sit there in 6 different ways. How? He can choose the first one, second one, third one, fourth one, fifth one, sixth one, right? So the second person, for the second person, there will be 5 different ways, right? How? Say the first seat is occupied by the first person, so there will be total 5 options left. Similarly, for the third person, there will be 4 and so on. For the sixth person, there will be only one way or one option, right? So how did we count that the first person has 6 different ways? As we can see that sitting here, the first person will see 5 empty seats to his left. If he would sit here, he would see the 3 empty seats to his left and 2 empty seats to his right. And similarly, if he would see here, he would see 5 empty seats to his right side. So when a person changes his position, he gets a different view, right? So in this case, in circular permutation, what will happen? For example, say the first person sits here in this place. If he sits here, he would see 3 seats in front and he would see 1 empty seat to his left and 1 empty seat to his right. Let's change the position of the first person. So if he sits here, he would see 3 seats in front of him which are emptied. He will see 1 empty seat to his left and 1 empty seat to his right. And similarly, if he changes the position and sit here in this position, he will get the same view. So in this circular permutation, we can see that for the first person or the first element, no matter how he changes its position or his position, the view will be same. It means that for the first person, the total number of ways in which he can sit will be one way. Why? Because all of the seats are empty, and if he sits somewhere, he will get the same view every time. Okay, for the second person, say this is where the first person has sat. So the second person, if he wants to sit, he has 5 options left, and if the second person sits here, he will have the first person to his left and there will be 3 empty seats in front of him and he will get an empty seat to his right. And if the second person changes his position, like here, if he sits here, he will get in 2 sides 2 empty seats, here and here 2 empty seats, and he will see the first person in this position right here. Okay, so it means that after the first person being seated, the second person can change his position, and for each change he will get different view. It means for each different options he will see or create different permutations. So that for the second person, since there are 5 empty seats, so there will be total 5 ways to sit. For the third person, there will be 4 different seats available, and he will get different views sitting into those 4. So there will be 4 options. And similarly for the fourth person, there will be 3 ways, and for the fifth person there will be total 2 ways, and at last for the sixth person there will be total 1 ways. So if we want to count in how many ways these 6 persons can sit around a table, will be 1 into 5 into 4 into 3 into 2 into 1, according to the multiplication rule of counting. So there will be total 1 into 5 into 4 into 3 into 2 into 1, that is 1 into 5 factorial ways. And as we can see that there were total 6 elements, and we get 6 minus 1 factorial different ways in case of circular arrangement, right? So if we want to generalize this situation or scenario, we'll see that if there are total n different elements to be arranged around a circular table, then for the first element, this is the first element. For the first element, no matter which set or which position it chooses, the view will be same, because as we saw there, for the first person being seated, he always got 3 empty seats in front and 2 empty seats in his 2 sides. So it means for the first element, out of the total n elements, for the first element the number of option or number of different ways will be only 1, because no matter where it is situated, the view will be same. For the second element, there are total n minus 1 different permutations. Why? Because after the first element being fixed, the position of second element always matters. And for the third one there will be n minus 2 options. For the fourth one there will be n minus 3 options, and like this. At last for the nth element there will be only 1 option. So in how many ways can we arrange n different elements around a circular table or in a circular fashion? There will be 1 into n minus 1 into n minus 2 into n minus 3, at last up to 1. It means n minus 1 factorial. So this is how we circular permutation is actually different from linear permutation. For linear permutation, in linear permutation, if we have n different elements, we can arrange them in n factorial ways. And for circular permutation, if we have n elements, it will be arranged in n minus 1 factorial ways. So if I ask you that you have given 11 different elements to arrange in a circular fashion, so in how many ways can you do that? You can do that in n minus 1 factorial ways, and here n equals to 11, that means 11 minus 1 factorial, that is 10 factorial. So now we know how to determine the total number of permutations for circular arrangement of n elements, right? So in this case, we'll see a special case of permutation with same elements. So let's say, what if you are given r elements to arrange in r slots where k number of elements are same? But what does I just say here? Let's say that here there are a 3-letter word, dog. So if I ask you in how many ways can you arrange these 3 letters, this is very simple. This is linear permutation. So there will be 3 factorial equals to 6 different ways, right? Okay. Now the word is egg, E-double-G. So there are 2G and 1E. According to the rule of linear permutation, these 3 letters are supposed to be arranged in total 3 factorial or 6 different ways. So let's check if our answer is correct. We can arrange them in another GEG permutation or GGE, this permutation. So is there any more permutation that we should write here? No. So since we were supposed to get an answer of 6, but we got here only 3 different ways. Why do you think it happened? Actually, it happened because we had 2 2G here, right? 2G here. So this is why it happened. So as we can see here that for 3 different elements we got 6, and for 2 elements being same we got 3 ways. So can we write here that 6 ways divided by 2 equals to 3, and can we rewrite this as 6 divided by 2 factorial equals to 3? So from this expression we can guess something. What it is? If all of the elements are different like this, then the total number of permutations will be n factorial, right? And if two of them here, two of them are same, then we may have to divide the total number of permutations, this one, with the factorial of number of same elements. So there were 2 same elements, we divided it by 2 factorial. So let's check another case. For example, say there are 1, 2, 3, 4. These 4 digits given. So in how many ways can you rearrange them? You can arrange them in total 4 factorial or 24 ways. Simple. But if you were given 1, 2, 2, 2, instead of here 1, 2, 1, 2, here you are given 3 2s. So will the result be same here? No, because if we try to rearrange all of them, what do we get? 1, 2, 2, 2, 2, 1, 2, 2, 2, 2, 1, 2, 2, 2, 2, 1. So here we can see there are only 4 different ways in which we can arrange these 4 elements. And why so? As we can see that here there are 3 2's, right? 3 2's. So here we got 24 ways. 24 ways total for all of the elements being different. So if we divide this total number of permutations by the factorial of same number of elements, that is 3 factorial, we get 24 by 6 equals to 4 ways. Students, this is interesting. Didn't we just get there these 4 ways? Yes. So we can say that if there are R elements, and we are given R slots for arranging them, and if K number of elements are same, then we can have the total number of permutation R factorial divided by K factorial. And can you just guess why it happens? We can see a generalized case here. How is it so? For example, say good is a word. If we want to know in how many ways we can have different permutations of the word good, let's say that English alphabet have 2 different letters like O1 and O2. So here O1 and O2 are 2 different letters, right? So fixing the position of these 2, we can rearrange this permutation like this: O2, O1 and D. See here, G01, O2D, this is a permutation, and G02, O1D, this is another permutation, right? But in the real, see, these 2 and 1 makes no sense, right? So these two permutations refer actually 1. So from where did we get these 2? Because there are 2 same elements. So each 2 factorial permutations refers to 1 permutation. So if there are k number of same elements, k factorial different permutations will refer to 1 permutation. According to the unitary method, 1 permutation would refer to 1 by k factorial number of permutations, and total r factorial, since there total r number of elements, r factorial permutation would refer to r factorial divided by k factorial number of ways. So in here we get that if we have r different elements to be arranged in r different slots and k same elements, so there the total number of permutations will be r factorial divided by k factorial. So I think we can solve another problem from here. If I ask you to rearrange or arrange all of the letters of the word excessive, right? So we can see here that there are 1 2 3 4 5 6 7 8 9 total 9 elements, right? So all of these letters, if they were different, they could be arranged in 9 factorial different ways. And here we get that there are 3 e's, right? 3 e's. So since there are 3 e's, so we'll divide 9 factorial with 3 factorial, and we can see here that there are 2 s's. So it means we'll have to divide it by 2 factorial. So the total number of permutations will be 9 factorial divided by 3 factorial to 2 factorial. Okay, so here we can see another example from using circular permutation, that for example, say there are 17 people in a dinner, okay, and Mahbub and Sherman are couple. So they want to sit beside each other. So if I ask, in how many ways can you arrange these 17 people around a circular dinner table where Mahbub and Sharmin will sit always next to each other? So to solve this question, if you just write there 17 minus 1 factorial or 16 factorial ways, it won't follow the condition stated above, right? Okay, then we can say that, say Mahbub and Shermin, these two elements make 1. So now there are total 16 elements, and according to the rule of circular permutation, they can be arranged around a circular table in 16 minus 1 factorial ways, right? And as we can see here, there will be said there are a1, a2, a3, a4, and it will go like this, and at last there is ms, one element here, right? So here we saw that Mahbub sat to the right of Sharmin, and do you think if we change the relative position of Mahbub and Sharmin like this, S and M, then for Mahbub sitting to the right of Sharmin, we get total 15 factorial different ways, and for Sharmin sitting to the right of Mahbub, we'll get another 15 factorial different permutations. So the total number of permutations for this problem will be 2 into 15 factorial. So among these 17 people, there will be 2 into 15 factorial different permutations in which Mahbub and Sharmin can sit beside each other around a circular dinner table. Thank you.